Hello everyone, I'm Hong Wong and I'm from the Department of Civil and Environmental Engineering at Imperial College London. I'd like to start by saying a huge thanks to the organizers for their kind invitation. It is a pleasure for me to contribute to this short course on multi-scale cracking of concrete materials. Now the focus of this session is on microcracks, their characteristics and influence on mass transfer properties and durability of concrete. So as you all know, concrete is weak in tension and therefore it has a tendency to crack when subjected to tensile stresses. Now the cracks can be broadly classified as either structural or non-structural cracks, and they come in different shapes and sizes. They occupy a wide range of length scales. Now structural cracks, as the name implies, occur due to external loading. So for example, flexural cracks that form on the beam that is subjected to bending, shown in these photographs here. So these cracks tend to be larger than 100 microns. They're considered as microcracks, and we control them by providing reinforcing steel during structural design. Now these cracks are obviously important, but I'm not so interested in them. I mean, what I'm more interested in are the non-structural cracks, which are caused by volume changes that occur throughout the life of the structure. So this excellent diagram here from the Concrete Society shows the different types of non-structural cracks, how they look like, and where they are likely to be found. So for example, concrete can crack at early ages due to excessive bleeding and settlement over steel reinforcement over deep sections, or due to rapid early age drying and plastic shrinkage. Now, cement hydration releases heat, and the temperature rise can be substantial in thick concrete sections. So the thermal expansion and the subsequent contraction and cooling can also potentially cause cracking. Now, other factors that cause cracking include drying shrinkage and degradation mechanisms such as reinforcement corrosion, frost attack, sulfate attack, alkali aggregate reaction, and so on. In most cases, the volume changes that occur within the cement paste itself at the microscale. So usually it is the cement paste that shrinks or expands due to the factors listed here. But the volume changes are restrained by rigid inclusions, such as the coarse and the fine aggregate particles that are inert and do not shrink or expand as much as the cement paste. In other cases, the cement paste is restrained by other parts of the structure that are also changing at different rates. So these produces non-uniform volume changes. They result in local tensile stress concentration that can lead to very fine, random and closely spaced microcracking, such as the cracks shown in this backscattered electron micrograph taken from an actual structure that has suffered severe degradation only after several years of operation. So one can see that the microcracks occur mainly within the cement paste, where the volumetric changes occur, and these volume changes are restrained by the aggregate particles. Now, personally, I find the microcracks very interesting because they are small and not readily detectable. So they are complex, heterogeneous, and spatially variable, and many factors can influence their initiation and propagation. More crucially, they are very difficult to control and eliminate by structural design alone. In practice, the microcracks may affect water tightness, may affect the serviceability and the function of many structures that rely on the ability of the concrete to act as a barrier to flow. So for example, in water retaining structures and pipelines, or structures that are designed to keep water out, such as basements, tunnel linings, and claddings. And furthermore, cementitious materials are used to store hazardous waste materials for very long periods of time, where the potential leakage caused by microcracking could be disastrous. So in addition, the microcracks could act as major pathways for ingress of aggressive species, such as shown here. increasing the transport properties of the concrete cover beyond what we would normally expect from the mixed design and curing age. And all these could accelerate deterioration mechanisms, leading to premature failure, loss of function, or service life. And although for a long time, people have known that microcracking occurs in concrete and suspect that they might impact engineering properties, now to our surprise, there's actually not much research that has been carried out to study them in a fundamental and systematic manner. The influence of microcracks on mass transport and durability of concrete is not well understood at all. And part of this, the reason is because they are very small and they are difficult to detect. The microcracks are heterogeneous and spatially variable, and this complexity is compounded by the lack of good characterization techniques to study the microcracks at sufficiently high resolution and representative volume in order to isolate and characterize and measure their effects. So decoupling the effects of microcracks is not straightforward. And this is because other phases within the microstructure also contribute to mass transfer processes. For example, the capillary pores, the interfacial transition zone, and the pore structure and moisture state within the calcium silicate hydrates. And the overall transfer property is dependent on a number of interacting factors that are very difficult to separate out. So for example, when we dry concrete from a saturated state, we find that the largest pores will empty first, followed by successively smaller pores. So the degree of saturation decreases, but the volume and connectivity of the accessible porosity increases. And at some point, the calcium silicate hydrates collapses and densifies. The pore structure coarsens, and shrinkage of the cement causes microcracking when restrained. So all of these can influence mass transport properties, and we need to decouple their effects because understanding how microstructure influences transport is important for developing more durable and sustainable concretes and service life predictions. But the question is, how do we decouple these? So in recent years, we have been doing quite a bit of work on characterizing microcracks caused by drying shrinkage and autogenous shrinkage using experimental mass transport testing, such as those shown in this slide here, to study the flow of gases, the movement of water, and dissolved ions. And we combine this with a range of imaging techniques to characterize the microcracks in 2 and 3 dimensions to measure their width and length distribution, their volume fraction, density, orientation, and so on and so forth. And we include also numerical modeling to simulate the microcracking and the flow through the cracked microstructure in order to improve our understanding of the nature of the microcracks, their impact on transport processes, and to develop mitigating strategies. So we've looked at a range of pastes, mortars, and concretes with a range of binder types, water binder ratios, aggregate types that have been cured and exposed to shrinkage for up to 4 years, which is the limit of a typical PhD in the UK. Now, I won't go through the details of the experiments and the developed methods. So there's no time for all that, and you can look up the published papers if you are interested. So in this session, I just would like to focus on some of the key findings that I think are particularly relevant. So in one series of experiments, we exposed saturated samples to 4 drying regimes to induce varying degrees of microcracking. So regime A here is a gentle stepwise drying and gradually decreasing relative humidity at room temperature until the sample reaches equilibrium. And as you can see in this graph here of water content plotted against drying period, there's a gradual decrease in moisture content over drying time. Now, regimes B, C, and D are more severe drying regimes at lower humidity and elevated temperatures to induce a much more rapid mass loss. And as we dry the samples, we measure the resulting microcracks and transfer properties at every drying step. So here are some example fluorescence images showing how the microcracks look like on the surface exposed to drying and on the cross-section of the sample. And what we observe is that the concrete undergoes significant amount of drying of microcracking. The cracks initiate at the exposed surface where drying shrinkage is the highest and form a typical mat cracking pattern on the surface. The cracks then propagate inwards, approximately perpendicular to the drying surface, and occasionally they may branch out or propagate around hard aggregate particles, forming matrix and bonding cracks. Therefore, the appearance of microcracking on the exposed surface is very different compared to that on the cross-section. But it's worth noting that the majority of these cracks occur within the first couple of millimeters or so from the exposed concrete surface. Therefore, drying shrinkage induces shallow microcracking that are concentrated near the exposed surface. We found that even in samples that were gently dried at room temperature, microcracks occur. But the size, the density, and the amount of microcracking increases with severity of drying, as one would expect. So here is an example of a frequency distribution diagram of the measured crack width plotted against the frequency. So the crack widths ranges from about 1 micron to about 60 microns, with the majority of the cracks having widths of less than 10 microns. So these are very fine and distributed cracks. And here is another example of a frequency distribution diagram for the measured crack length. Again, it shows that the amount of microcracking and the length of the microcracks increase with drying severity. The majority of the cracks have lengths of less than 100 microns, and therefore drying shrinkage induces microcracks that are very fine and very short, and they are concentrated near the exposed surface. In another series of experiments, we sealed the samples in room temperature to induce internal drying, i.e. self-desiccation and autogenous shrinkage. Now, similar to the external drying experiments shown previously, the mixed variables include binder type, water binder ratio, maximum aggregate size, and so on. And we monitored the samples for nearly 4 years by measuring the linear deformation, i.e. the linear shrinkage, the microcracking that formed, and the transfer properties over time. So here we see that the shrinkage increases with time. It increases in low water binder ratio systems and in systems that contain supplementary cementitious materials such as silica fume and GGBS. The shrinkage also increases in systems that contain larger aggregate particles. Now, the mixes that contain shrinkage reducing admixtures, which are denoted as SRA here, displayed the lowest shrinkage. So this demonstrates the effectiveness of SRA in mitigating shrinkage. Now we then characterize the microcracking that formed in these systems. And here is an example using X-ray microcomputer tomography to obtain the 3-dimensional image of the sample, which we then process using image analysis to extract first the aggregate particles, then the voids, and then finally the microcracks. And what we observe is that the self-desiccation or autogenous shrinkage causes microcracking to occur pretty much all over the place, spanning the entire sample and forming highly interconnected structures. The severity of the microcracking increases with increase in the magnitude of shrinkage. And therefore, concretes that are the strongest, i.e. concretes with the lowest water binder ratios, containing SCMs, supplementary cementitious materials, will experience the greatest amount of microcracking. So for example, here we have a series of three-dimensional views of microcracks extracted from X-ray CT images of concretes that contain silica fume at a range of water binder ratios from 0.2 all the way up to 0.45. Okay, and we can see that the system with the lowest water binder ratio here experienced the most extensive microcracking. We can also see that the autogenous shrinkage-induced microcracks are larger in size, they're more densely distributed, and they are more interconnected compared to externally drying-induced microcracks. So these cracks, they occur throughout the samples, whereas the drying-induced microcracks occur in the first several millimeters of the exposed surface, as discussed previously. Now, this slide shows the cumulative volume fraction of the microcracks plotted against microcrack width for different water binder ratios and for different binder types. So again, we can see that the systems with the lowest water binder ratio containing supplementary cementitious materials experience the most extensive microcracking. And the average width of the microcracks range from about 15 to 100 microns, which is much larger than what we have measured for the case of drying shrinkage-induced microcracking. Here we show that the microcrack volume fraction plotted against autogenous shrinkage and against total accessible porosity. Again, this shows that the degree of microcracking increases with shrinkage, and that the denser systems at low water binder ratios and containing SCMs show the most severe form of microcracking. However, the use of SRAs, the use of shrinkage-reducing admixtures, again, is highly effective in mitigating the amount of shrinkage and therefore decreasing the amount of microcracking. So then the question is, what is the impact of microcracks on mass transport? Some may think that because these cracks are very small, so surely they can't have a huge effect. All the microcracks are small relative to the structural cracks, but they are at least 100 times larger than the capillary pores and many more orders of magnitude larger than the pores within the calcium silicate hydrate. And because the cracks are highly interconnected, they can provide major pathways for transport processes to occur. And so we carried out a series of experiments to try to isolate the microcracks and to study their significance on mass transport. One of the first experiments that we did was to use a simple setup shown here to visualize the effect of microcracks on water absorption. So here we expose one side of the microcrack sample to a water containing a special dye. Then we use fluorescence imaging to track the ingress of water in real time. Here is a series of fluorescence images captured on the same sample after different exposure periods to water absorption. And the sample was previously dried to induce surface microcracking. What we consistently see is that the initial water uptake, so here at 9 seconds, is dominated by rapid absorption into the surface microcracks. And this causes a highly irregular penetration front. And over time, the microcracks becomes fully saturated. And once the microcracks become fully saturated, then the subsequent water uptake occurs mainly through the non-cracked regions. And the apparent effect of the microcracks diminishes over time. The subsequent penetration front then becomes more uniform until the sample reaches full saturation. Now, when we combine image analysis with conventional gravimetric measurements of water absorption against square root of time, so this is the conventional sorptivity test, we find that the microcracking produces a form of anomalous absorption behavior in the square root of time plot. So instead of getting a nice straight line that we would expect from classical unsaturated flow theory, we observed a non-linear sigmoidal behavior. And so we did some measurements that showed that this anomaly increases with severity of microcracking. Therefore, the microcracks accelerate initial absorption, and this in turn distorts the square root of time plot. For gently dried samples where there is less surface microcracking, we see that the water absorption front is much more uniform over time. Hence, the water uptake is less affected by surface microcracking, and this produces the classical bilinear water absorption plot versus square root of time, where now the sorptivity coefficient can be determined from the slope of the initial absorption. In another experiment to detect the effect of microcracks, we applied a small confining pressure during transport testing in an attempt to compress the microcracks and to measure the effect of the confinement on flow properties. So here is a photo of the transport cell where we place a pressure-sensitive film on the sample surface that changes its color depending on the applied pressure. And we carried out the transport testing at increasing level of confinement. Now the graphs here show the measured diffusivity and permeability plotted against confining pressure for different samples. Now we also did some image analysis to see the effect of confinement on the microcracks and to correlate that to the measured transport. And we see that the confinement causes the microcracks to partially close, and this causes a significant drop in flow, especially for the case of permeation. However, the microcracks seem to have a less influence on diffusion because diffusion is governed by total porosity, and the microcracks account for only a small fraction of this. It is also worth noting that the applied confining pressure here is small relative to the strength of the concrete. But real structures are subjected to much larger stresses, and therefore one may deduce that the effect of microcracks is probably small in structural locations that are under compression, but this increases in areas that are in tension. So I think this highlights the importance of measuring transport under realistic loading conditions, but it is not an easy experiment to do, and we certainly need more data and effort in this area. Now, the next set of experiments concern size effects induced by microcracking. So transport tests are normally carried out on samples that are about 25 to 50 millimeter thick. The maximum aggregate size in mortars and concrete is typically up to 20 millimeters, say, and therefore the T to MSA ratio covers a wide range from about 2.5 to 20. Now, most codes of practice for mass transport testing recommends testing samples at a ratio at around 3. But we know that the drying-induced microcracking are concentrated near the exposed surface. So the question is then, what is the effect of this ratio on the transport properties of microcrack concrete, and whether or not the recommended ratio is appropriate? Here we plot the measured transport against the T to MSA ratio for diffusion, absorption, and permeation. And we can see that there are no significant size effects for diffusion, absorption, or porosity. The results are very similar regardless of whether a thin sample or a thicker sample is tested. Now, however, for permeability, we can see that there's a huge size effect where the measured permeability decrease with increase in T to MSA ratio. Or in other words, the measured permeability increase significantly with decrease in T to MSA ratio, especially when this ratio is less than 10. And this is consistent with what we saw earlier with permeability testing being more sensitive to the microcracks compared to the other transport properties. The size effect is also seen in the measured crack width, length, and density, where data shows that the increase in these crack parameters will decrease in T to MSA ratio. So therefore, samples that are thin relative to the maximum size of aggregate inclusions will lead to a higher degree of microcracking, and this in turn increases the connectivity of the microcracking and therefore the measured permeability. In the next series of experiments, we looked at the effect of drying on transport properties. Now, it is well known that drying has a huge impact on increasing transport. And there are lots of data out there showing the effects of drying is greater than the other factors such as mixed composition, curing age, etc. Now, as explained earlier on, there are several possible reasons for this. For example, microcracking, changes to the calcium silicate hydrates, and so on. Now, because we are interested in the microcracks, we try to isolate this effect by re-wetting the severely dried samples. So re-wetting these guys here so that they then achieve a similar moisture content to that of the gently dried samples. So that now any residual effect on transport is most likely due to damages to the microstructure rather than to the degree of saturation. So in other words, we started by drying the samples using the same 4 regimes to induce varying degrees of microcracking. And then we introduced a re-wetting regime in the stepwise manner. And as before, we measured the transport property at every conditioning step. Now, I have to say that this is a very tedious and time-consuming experiment, especially for thick samples. And it's probably not something I would like to ask my PhD students to do ever again. But the data is very interesting, and here is an example for diffusion plotted against relative humidity for paste, mortars, and concrete samples. So A, B, C, D are the 4 initial drying regimes. The red and the blue arrows represents the drying and the subsequent re-wetting paths respectively. We can see here that the drying severity has a huge impact on transport. But on re-wetting, moisture content then increases via absorption and condensation. Microstructure becomes increasingly filled and blocked by moisture. The transport then decreases modestly and then rapidly drops to 0. Now, there is a significant moisture and transport hysteresis that occur over the entire RH range. And we also observed that concretes with SCMs consistently showed lower transport compared to the equivalent SAM1 samples at similar porosity. But these concretes, the blended concretes, they are more sensitive to drying, and the effect of microcracks is more pronounced on denser systems. However, when we replot the data against now degree of saturation to isolate the effect of moisture, what we see now is that the difference between drying and wetting curves decrease significantly. The curves now overlap, and the apparent hysteresis almost disappears completely. And if we look at the data carefully, we can detect a small residual effect of about less than the factor of 2 that we can attribute to the effect of drying induced damages on diffusion. Factor 2 here, factor 2 for the case of mortar, and also factor 2 for the case of concrete. Now, this is another set of data, but for permeability. Here, we see that the residual effect of drying induced damage ranges from a factor of 2 for paste and mortars to a factor of 4 for concretes. Now, this is clearly much higher than diffusion because pressure-induced flow is more sensitive to microcracks, as we saw earlier. And this is also consistent with our earlier observations that microcracking increases with increases in aggregate size, and therefore the residual effect on concrete is greater than that on mortars or paste. Now, of course, this is for drying-induced microcracks, which we know are shallow microcracks concentrated near the first couple of millimeters from the exposed surface. So what about the autogenous shrinkage microcracking, which we know from the slide shown earlier on that these microcracks are more extensive, they are larger, they are much more interconnected, and they span the entire sample. So we would expect that the effect of these microcracks on transport to be much greater, and indeed that is the case. So here we show the measured diffusivity, measured permeability, and water absorption plotted against autogenous shrinkage for different binder types after more than 3 years of sealed curing. And we can see that the use of shrinkage reducing admixture is highly effective in reducing the amount of microcracking and therefore the measured transport. This is the mix here with SRA, and similarly the mix with SRA is here, and then the mix for SRA is here for the case of subtility. The residual effect is close to a factor of 5 for the case of diffusion and absorption, but it's over a factor of 50 for permeation, again highlighting the sensitivity of pressure-induced flow to microcracks. Now, one final thing that I would like to mention is self-healing of cracks. So it is well known that cracks have a natural ability to self-heal over time in structures that are exposed to wetting. And there are many studies that have shown this effect. And here is one example done at Imperial, where we prepared cylindrical samples like this, and we produced a single through crack by tensile loading, which we then place into a test cell and a flow through assembly. Then we apply a pressure gradient across the sample, and then we monitor the flow rate over time. And here is some example of measured data of flow rate and cumulative flow plotted against time in the logarithmic scale, different mixes containing a single 0.2 millimeter crack. Now we can see that the flow rate increases very rapidly, and then it peaks at around 5 minutes and then gradually decreases over time to zero flow after several days in some cases, or after several hours even in other cases. So this is crack healing, and crack healing can be attributed to a number of mechanisms such as further hydration, swelling of the hydrates, carbonation-induced precipitation, or blockage of the crack by loose debris, and so on. But the time it takes for complete healing depends on the number of factors, which I won't go into detail for this talk. The key message is that small cracks can heal. This is a 0.2 millimeter crack. And therefore, microcracks, so cracks that are smaller than 0.1 millimeter, will heal even faster. But whether or not this is sufficiently reliable to mitigate the effect of microcracking and the impact on long-term durability remains an open question. So here are some concluding remarks and key takeaway messages. So I hope that I've given you a good overview and evidence that microcracks exist in concrete. Now, we observe that external drying causes surface microcracking that are less than 100 microns in width, and they are concentrated within the first few millimeters from the surface. But self-desiccation and autogenous shrinkage produces much more extensive microcracking throughout the entire sample. The microcracks are difficult to eliminate by structural design alone. They can impact mass transfer properties and accelerate ingress of aggressive species. Drawing increases the mass transfer properties significantly. However, when the samples are wet, they display transfer hysteresis, and the residue is small once differences in moisture content have been accounted for. And if the cracked samples are then resaturated, then the residual effect becomes even smaller, and the cracks self-heal over time due to several possible mechanisms. We also saw that the use of shrinkage-reducing admixtures is highly effective in mitigating shrinkage microcracking and impact on transport. Lastly, it is worth commenting that most of the research on microcracking has been carried out in the lab on relatively small scale samples. And I think that more work is needed in this area, in particular on concretes containing supplementary cementitious materials and in field structures that are exposed to real loading and environmental conditions. So before I end the talk, I just would like to say thanks to the organizers again, and to acknowledge the contributions from the following individuals who are my previous and current PhD students, and also long-term collaborators. I would also like to acknowledge the following funding agencies that have supported various aspects of the research. Many thanks for listening in, and I'm happy to take questions and look forward to our discussion. Cheers.